All right, well, thanks everyone for attending. I'm excited to be talking today about a model of divergent adaptation using sister species data sets. I'm working on this model with my advisor, Jason Weir, seen here, oddly enough, in an area completely devoid of insects. He just really likes that net. Models and analyses I'll be talking about today will be available in our package Diverge. It's not available for download from Grand today, but I'm hoping it will be by the end of this conference. And I'll be tweeting about it when it comes out. But the topic of the day is divergent adaptation between populations and lineages, and specifically between closely related lineages like sister species. And this is simply when lineages adapt in different directions in one or more processes. The process is common. It's probably pretty much ubiquitous, given that no two environments are exactly alike. So whenever you have spatial separation, there's probably some degree of divergent adaptation occurring. But we know of it as an important process because it can be a powerful driver of speciation. And this is not a new idea. It's the essential thesis of The Origin of Species in Darwin and Wallace's joint paper. But in the modern understanding of it, we know it as directly responsible for the evolution of both pre- and post-zygotic reproductive isolation. And there are three lines of evidence behind that claim. The first are a series of case studies conducted since about the 1990s on incipient species pairs. These are young, recently diverged pairs of taxa, such as some of the examples I've shown here. And what those studies have shown is that this divergent adaptation can cause assortative mating within ecotypes, and it can also cause hybrids with intermediate phenotypes to have reduced fitness in the wild. So this beginning of pre-zygotic and post-zygotic reproductive isolation. There's also some evidence from laboratory studies in which divergent selection has been induced in lines of fruit flies and things like E. coli, and there's been some evidence of assortative mating that has come about from that. The last line of evidence is an association study that has shown a consistent positive correlation with ecological and genetic differentiation. So the more ecologically diverged sister species are, on average, the more genetically diverged they are as well, suggesting there could be some sort of isolating component to that ecological adaptation. So it sounds like we have a pretty solid understanding, solid grasp of the process. There's actually some really fundamental questions that we don't know the answer to, and that can have a pretty profound understanding, or effect of our understanding on diversity patterns. And the most important one is, how important is the process to speciation generally? And we actually don't know this. So we have this association study, but we don't know the answer to this question in terms of what proportion of sister species today were produced by the process of divergent adaptation or ecological speciation. And this is despite a very clear prediction, which is that if divergent adaptation is important to speciation generally, then sister species in general should be ecologically differentiated. And you should often be able to see that in terms of functional traits, ecologically important traits. And sometimes it's quite obvious that this has been the case, as in the case of benthicolin and stickleback. And sometimes it's less obvious, as in these ant birds from the Amazon, that despite 4 million years of divergence and near complete reproductive isolation, have no outward signs of adaptive differentiation whatsoever. I should point out that these birds are not an exception, that this fits a common pattern of Amazonian understory birds. And there happen to be very many Amazonian understory birds. So these non-differential adaptive processes are likely contributing in a meaningful way to species richness, at least in some areas. And this has recently been reviewed in a paper that I quite enjoyed and I recommend reading, The Ecology of Non-Ecological Speciation and Adaptive Radiations. Some other outstanding questions are, how does the process vary through time, especially with respect to speciation? Does ecological divergence occur at the beginning of the speciation process, and does it drive it? Or does it occur only later, after a period of time in isolation, when perhaps one or both populations colonize new adaptive zones? And finally, how does it vary across biological and ecological variables? So are some species more likely to undergo this process, perhaps because of some chromosome arrangement or some structure like a pharyngeal jaw? And are some environments more likely to induce this in the taxa that live there, like forests versus high desert or something like that? And ultimately, what we want to know, the answers to these questions help us explain broad-scale diversity patterns. But in order to get any of these questions, we have to move beyond the careful study of some model systems. And what we really need is we need to look at it through a comparative framework. We need to look at how the process occurs over many pairs of taxa, so many sister species, and ideally over some longer timescales. So we're not just looking at incipient speciation anymore, but we want to see timescales relevant to the speciation What I mean by that is timescales that would produce what we would likely call full species today. And the central problem of the talk is that we lack an explicit comparative framework for tested divergent adaptation between lineages over speciation timescales. We just don't have models for that just yet. What we do have are whole tree phylogenetic approaches that look at adaptive divergence. So this includes the early burst model and lineage through time analysis and disparity through time analysis. And what these tests do is they look for signals of diversity dependence. So from the perspective of a whole clade, does the rate at which lineages are added and morphological diversity is added, does it decline with time as ecological opportunity is exhausted? And these models are really good for testing things like adaptive radiation from the perspective of a whole clade, but they're less well suited to looking at the process of divergent adaptation as it pertains to the splitting of one lineage into two. And for that, what we really want is an analysis that can use data sets comprised of sister species or sister lineages. So I'll briefly introduce the sister pair approach in comparative analysis. This is an outdated phylogeny I'm using of Anolis just for illustrative purposes. Whole tree phylogenetic approaches would look at all the tips of this tree, and they look at the dynamics of evolution as it occurs from the root to the tip. So looking at how the whole clade is produced. In the sister tree approach, we take a phylogeny or several phylogenies, and we identify the sister taxa at the tips that are joined. And our unit of interest is now this the evolutionary divergence that has occurred within these sister species since the time of their divergence. So the data that we're using are sister pair contrasts and traits of ecological importance. There's no ancestor state reconstruction involved. Where the metric of interest is divergence, the ancestral state is 0, an ancestor hasn't diverged from itself. It requires well-resolved and dated phylogenies. So the method I'm going to be talking about is only good for those taxa for which we have species-level resolution. And it's useful for investigating links between microprocesses and macro patterns over early macro timescales. What I mean by that is you're not going to be looking at dynamics of evolution since the Cretaceous. We're going to be looking at how things have diverged towards the tips of trees since the most recent speciation events. We have existing models that look at this sort of divergence, but they do, and they address adaptive divergence in a very indirect way, as I'll try to explain right now. So the models are based on analysis of continuous ecomorphological traits, things like beak shape or fin area or petal width, and they model evolution as a stochastic process, such as Brownian motion or the Ornstein Uhlenbeck process. I'm sure there are many of you here that are very familiar with these processes, but I'll just go over it real quick. Both processes model the evolution of these traits as random walks through continuous time. And they differ in that the Ornstein-Uhlenbeck process puts a bound on that randomness. So it bounds the random walk around a value that we interpret as being a phenotypic optimum. So we interpret it as being something analogous to an adaptive peak in OpenSea. And the trait differences in the current approaches, are modeled as random deviation in evolutionary trajectory. What I mean by that is that the way that the models currently work is that divergence between sister species is modeled as the difference between two replicate runs of a single stochastic process. So imagine we have one sister species here, or one species, yeah, one sister species. So there's two lineages, they're evolving randomly through time according to the same process. Their divergence also varies through time, and at the end of 5 million years, we have some positive divergence. Species 1 has a higher phenotype value than species 2. In this example, it's a different sister pair, but it's the exact same stochastic model. By chance, they've got a greater divergence through time, so the divergence is increased much quicker. And you can imagine if we have many replicates and we have a whole data set, in this case we have 15 sister pairs, we get a distribution of divergences through time. And if you cut that at any time slice, you can get a distribution that has some trait divergence. And this can be used as the basis for likelihood-based model fitting and parameter estimation. In the Ornstein-Uhlenbeck process here, what's important to note is that in the existing approaches for dealing with sister pair data sets, the theta value, which is the phenotypic optimum, is always set to 0, and it's set to 0 for both sister species. So what that means is both lineages in a pair are being constrained around the same optimum. So what this is really modeling is something like phylogenetic niche conservatism, or parallel adaptation, but not divergent adaptation. And importantly, these processes are then used to infer sort of evolutionary history. If you have a data set comprised of species like stickleback on the left, you're likely to estimate a higher dispersion parameter for a stochastic process. And then you can start explaining that in terms of why divergent adaptation is greater for that set. But divergent adaptation is not what we've actually modeled, right? Because these are entirely random deviations. So again, divergence between sister species in these cases modeled as a difference between two replicate runs of a single process. So that means trait differences entirely randomly generated. Basically, it's the stochastic component of the stochastic process model that's produced our differences. But of course, divergent adaptation is not a random process, right? These stickleback, with 20 years of research on stickleback or more, indicate that they've arrived at their phenotypes through selection to different phenotypic optima. One associated with a benthic niche, one associated with a glynetic niche. So there's a deterministic aspect to this. And for the rest of the time, I'll be talking about a model for this that we've come up with. We call it the DA model, DA for divergent adaptation. And quite simply, we just don't constrain lineages to be evolving around the same optimum anymore. Lineages in a pair can evolve toward different optima. So they're allowed to evolve according to their own stochastic process. It's an OU process, so there's an optimum involved, but that optimum is different. They differ only in the position of that optimum. And so now divergence is non-random. The nice thing about this approach is we can essentially allow every lineage in the data set to have its own phenotypic optimum, and we don't need to estimate it. Because again, our data are differences between phenotypes. And so what we're really interested in is the distance or the difference between these phenotypic optima, which we represent here with the parameter psi j. And we derive this quite simply from the fact that a phenotype undergoing a stochastic process, if it's indexed at any time, that trait is a random variable with a normal distribution. So if you're allowing two lineages to evolve independently, the difference between them is also a random variable with a normal distribution. The expected value of that normal distribution is the difference between the expected values of the individual lineages, and the variance is the sum of their variances. So the expression right here gives the expected value of a lineage undergoing, or part of a trait undergoing Ornstein Uhlenbeck process. If we subtract one of those from another one with a different optimum and nothing else changes, then we get this expression here for the expected value of their difference based on the distance between their optimum. Right? And that's really the metric of interest here. So we call that psi, and that becomes the primary thing that we're concerned with in the analysis of divergent adaptation using these comparative data sets. We can now return to our analysis with data and start asking things like, do you get a non-zero psi value, distance between optima, given all data sets? And this can help us answer questions like, how important is the process of speciation generated? If you have a large data set of more or less randomly selected sister pairs, are you going to estimate a model with a psi value that's greater than 0? Whether or not you can will depend on the distributions. Obviously, the key difference between the distributions is that in the divergent adaptation model, the density around 0 is hollowed out. So when it's just completely random, a lot of species by chance will have no divergence after a certain period of time, and that becomes much less likely under the divergent adaptation model. And that's sort of the basis for model selection. There are some sort of exciting extensions to this model. One of them real quick is how does it vary through time? And you can imagine a lineage undergoes an adaptive shift at some point in its history. That changes the relative distance between optima. We can model that as a breakpoint. The key question becomes whether the distance between optima before the breakpoint is greater or less than the distance between optima after. And a quick note on this is when you're doing this, you need a data set that contains both pairs that have and pairs that have not experienced that shift in order to accurately estimate it. And one potentially fun application for it is character displacement. I've been working on this one for a particularly long time, and I'm running out of time, but if anyone wants to talk about that, I'll be happy to chat after this. And so I should wrap up, but just a quick summary. Divergence between sister pairs can be modeled as pulls toward alternative optima, so it's no longer completely randomly generated. The distance between optima is psi, which is the extent of adaptive differentiation. It can help us in the comparative analysis. Outstanding questions can be addressed with some model extensions, which I'm happy to talk about after this. And this DA model contributes to a more complete suite of process models, because when you can combine it with the original OU, the single process, and a Brownian motion one, you're now looking at phylogenetic niche conservatism, divergent adaptation, and some random trait evolution as well. And with that, I'll finish off. I'll plug real quick. This is a magazine that some grad students at U of T have put together, and you're welcome to download it. And some of the editors of this magazine are talking today, including my colleague James Santangelo, who goes tomorrow. So thanks very much.